Okay, so radioactivity, we are going to start with what is radioactive, what is a radioactive nuclei, and that's going to be a nucleus that is unstable. Things that are unstable are radioactive, they fall apart, they spontaneously decompose into other things. So nuclear chemistry is very different from all the other kinds of chemistry. We are specifically going to talk about the nucleus, right? Most other chemistry happens within the electrons. We are talking about the nucleus now, so not so much about the electrons. So nuclear energy is really important. You've probably heard of nuclear energy before. We're going to use it a lot. It's produced from radioactive nuclei. So when a radioactive atom actually breaks down, it might give off particles when it decays. It might break into other things. We do get radiation. We're going to talk about what that is. And we also get energy. We can use that energy, that heat energy, it's not a renewable source, but it is a source of energy. So we actually get about 20% of our energy in the US from nuclear energy. If we do it a certain way, we can make it so that it's going to be a little bit more productive for energy and have less waste. So I will talk about that later. So we're really talking about what's going on with the nucleus. So first of all, we have to understand what is in the nucleus, right? Protons and neutrons. Now, how many is going to tell us if something's going to be stable or not. So the symbols look like this. We write our element symbol, so like carbon, C, all of that. We put the mass number in the top left, and the mass number is the number of protons plus the number of neutrons. Now, when you look at the periodic table, that doesn't actually tell you the mass number of a nucleus. It gives you the average atomic mass for all of the isotopes. Okay, a mass number is actually the number of protons and neutrons, so it should be a whole number. Okay, there are different isotopes. And then the atomic number or the number of protons should go in the bottom left. Now, we're not so worried about the charge up here because we're not talking about the electrons, so the electrons don't really matter right now. Okay, so atomic number is number of protons, mass number is protons plus neutrons. Another term for these are called nucleons, so anything in the nucleus is also called a nucleon. Okay. So I mentioned isotopes. Isotopes are atoms that have the same atomic number, meaning the same number of protons, but different masses, meaning that they have different numbers of neutrons. So if they have the same protons, that means they're the same element because the atomic number tells you what the element is. But they can have different masses, which is why on the periodic table, you get those average masses. That's why there's decimals, because there's different isotopes of different elements, and those are like weighted averages. So each element on the periodic table has one or more naturally occurring isotopes. So for example, let's talk about carbon. Carbon actually can be carbon 12, carbon 13, or carbon 14, all naturally occurring, but one, carbon 12, is much more stable than the other two. And we're going to talk about carbon 13 and carbon 14. So usually there's a one that is more stable or more naturally occurring, but not always. And you can kind of tell from the masses on there which one is going to be the most stable. Carbon's mass is 12.011. Most of the carbons are carbon 12. Okay. Now, the ones that are unstable are called radioisotopes because they are radioactive. Okay. So an unstable isotope can also be referred to as a radioactive isotope or a radioisotope. So these decay processes, we are going to start writing decay equations. Okay, and these essentially show you what happens when a radioactive particle decays. So it says what you start with. So uranium-238. This is uranium that has 238 nucleons, essentially, protons plus neutrons. And uranium is number 92. It always says 92 protons. Okay, so uranium-238 is actually a very unstable nuclei, a radioisotope, if you will. So it's going to decay. And what it does is it decays by what's called alpha decay. And I get an alpha particle, which has a mass of 4. It's 2 protons and 2 neutrons. And I get thorium-234, which is has 234 protons plus neutrons. It's got 90 protons. Okay, so the terms for these that we need to know in this nuclear reaction are the one that we're starting with is called the parent nuclei or the parent nuclide, the one that is radioactive. And then it's going to decay, that's what our arrow is showing, into, it's going to give off some type of decay product, whether that be alpha, beta, gamma, we're going to talk about those, and another nuclei. So one that is a different element. In this case, thorium. That is called the daughter nuclei or nuclide. Usually that one is much more stable than the original. So it's going to decay by a process that makes it more stable. Okay, so this reaction is different than a chemical reaction, right? In a chemical reaction, we have to have the same elements on both sides and we have to balance the elements. That's not what's going on here. Okay, very different. We're turning one element into another element by a decay process. So the types of nuclear decay can release any of these types of particles, right? So there's an alpha particle. An alpha particle is a 4-2, and it can be represented by the alpha symbol here. Or technically, if it's 2 protons and 2 neutrons, that's just a helium nucleus because helium has 2 protons. So you can write 4-2 helium also. Either one is appropriate. Okay, these alpha particles are really big. They have a mass of 4, so they're high mass. They're very low energy. They move very slow because they're so big, and they're essentially just a helium nucleus. Okay, another decay product that we're going to talk about is a beta particle. A beta particle is like an electron. Okay, electrons have very, very small mass, almost negligible mass, right? And they have a -1 charge. So the way that we represent this is they have a mass of 0, so 0 at the top, and we put a -1 down here for the atomic number because that is going to affect how our charges kind of balance out. So in a nuclear reaction, an electron is going to look like this, or a beta particle is technically what we're talking about. So you can do it with a beta symbol. That's a capital beta. And that is a high energy, I put in quotes electron because it's like an electron, but it's not coming from the electron cloud. It's actually coming out of the nucleus. So when a neutron breaks down into a proton, what essentially happens is, if you think about it, a neutron is neutral, right? So it kind of has like a positive and a negative. They just balance each other out. Well, if you shoot out the negative part and you still have the positive part, now you are left with a proton and you just got rid of the negative charge. That is the beta particle. We just got rid of the charge. Okay. So that's what a beta is, when a neutron turns into a proton. And you don't have to be able to explain that, but that's essentially what's going on. We can have a gamma. Gamma is actually a ray, not a particle. It doesn't have mass. It doesn't have a charge. It's just a radioactive wave that is given off. Or a photon. Photon can be a wave or a little packet of energy, particle wave duality, all of that. I'm not going to talk about that, but it's a photon that's released very high energy. It's very impactful to you if you're exposed to a lot of gamma radiation. Not good. You can have a positron be released during a nuclear decay reaction. A positron is like that little electron, but it's got a negative charge, or sorry, a positive charge. I said that wrong. So we represent it like an electron. It's like a little positive electron, or you can use the beta with a +1 charge. Okay, so it's represented either of these two ways. It's like a positive electron. You might be like, well, then isn't that a proton? No, because it has hardly any mass. Proton has mass, an atomic mass, you have 1. An electron we call about 0 because it has such a small mass. So it's really like that positive charge part. So this is what happens when a proton turns into a neutron. So if you think about it, I got a proton, which is the same size as a neutron. If I just chuck the positive charge, I'm left with a neutron. So what it's doing what it's released as a positron is just getting rid of that positive charge. Okay, and then a neutron can also be a decay product, and this is how we represent a neutron, a 1, 0, n. It's got a mass of 1, no charge, and we just use a lowercase n. All right, so that's a neutron, mass of 1. So these are all of our potential decay particles.